Continuing with the cooling system, let's talk about the radiator. Now, the radiator's job is to transfer heat out of the coolant and into the air around the vehicle. And the key thing for that is to have loads of cold air in contact with the coolant. We can do that in two ways. One way is to have a big surface area of coolant touching the air, and the other is by putting lots and lots of air across that surface. Now, the radiator is made of two tanks. We've got a header tank at the top, we've got a bottom tank here, and between those two tanks is a core or a matrix, which is made up of lots and lots of little tubes that divide up the coolant into separate flows, and that gives it a bigger surface area. The radiator cools on basically the same principle as cooling this lovely cup of tea. If the tea sits in this mug, then only the top surface is able to exchange heat with the air, and so the tea is going to stay warm for 10 minutes or so. But if we take out the tea bag and split this tea across three saucers here, we have a much bigger surface area in contact with the air, so it's going to cool dramatically quicker. And no one likes cold tea or cold soup. The radiator core is made up of loads of thin water tubes, and the coolant flows down these tubes from the header tank to the bottom tank. If we take off the radiator cap, you can actually see the tubes just inside here. Now, the tubes are connected together by lots of metal fins. Those give greater strength, and they also mean that we've got more metal conducting heat away from the coolant and out into the air. Historically, radiators were made from copper or from brass. Today, the tanks are almost universally made out of plastic for the tanks and aluminium for the core. It's much cheaper to make it that way, it gives better performance, it's lighter, and for a production vehicle, it's absolutely more than enough performance at reasonably low cost. Now, solid aluminium radiators are available as an upgrade. They're pretty popular if you're doing racing modifications, this kind of thing. It gives a little bit of additional cooling through the tank because the tanks are made of aluminium. The whole radiator is made of aluminium, so you've got some heat loss through the tanks at the top and the bottom, and it's a bit more of a durable construction. This radiator uses a single row of tubes, and it's called a single row radiator. There's also a double row radiator or a triple row radiator. Using multiple rows of tubes that run backwards like this gives a radiator which isn't as long. Now, ideally, a radiator in an ideal world would be very thin like this and very wide and very tall with a huge frontal surface area in contact with the air. But that doesn't really suit the design of a modern vehicle which has a narrow front, a sleek body lines. So instead, you'll find that radiators increase the depth. But adding depth is not as valuable, it's not as effective at cooling as adding width and height, because as the air makes its way in, say it goes past the first row of tubes, it's warmed a little. By the time it hits that second row, it's already been kind of warmed up a little bit by the tubes at the front. So 2 rows, slightly less effective in terms of performance per row than a single row. And once you get above a 4-row radiator around that mark, the airflow starts to suffer as the air that hits the back tubes has already been warmed up by those at the front. In the US, there's a standard for a tube height that's about 1 inch. In Europe, it's about 16 mil. Obviously, that's going to depend on the manufacturer of the vehicle rather than where your house is. Also, we've got fins. So in addition to the tubes, we've got the fins that go between them. You'll find that there'll be serrated fins, all sorts of different ways of giving those fins a bigger surface area. A typical radiator is going to have about 14 fins per inch on the way down. And the density of those fins is important, so you might find that specified. A higher density of fins increases the cooling capacity. But too high a density and it becomes hard for the air to actually flow through the core. And the tighter these fins are here, the more at risk they are of getting bogged up, clogged up with dirt and bugs and general road grit. If we take a look, hold on a minute, if we take a look at an old radiator, you can see that over time the fins end up being gunked up and it loses the ability to conduct air through there. That's one way that a radiator wears out. Let's talk flow. Now, most radiators use a vertical flow of coolant like this one, with coolant coming in at the top and flowing down to the bottom. That's called a downflow radiator, and it's helped by natural convection because cool water tends to become denser and it sinks. But of course the coolant in here is mainly being pushed around by the water pump itself. So while this vertical flow, this downflow, is the most natural flow to have in a radiator, cars have become more aerodynamic and grills have become much lower and much wider. If you think about a classic high performance old car from the 50s or something, you'd be looking at a huge grille on the front, a big tall grille. Nowadays they're low and they're wide. So to make a radiator fit in that available space, we want a shorter radiator. And so some radiators adopt what's called a cross flow, where the coolant enters on one side and flows across the radiator to the other side. The reason for that is that although the radiator is the same size, you could have a radiator which was just this tall and you could have the coolant flowing down, but it would spend hardly any time in the radiator. It would just be passing from here to here in a very short period of time and then back around. And that's not as efficient as putting coolant through the radiator over a long period of time. So we want coolant to come in and spend some time losing heat in the radiator and then get back around. So it's more efficient for a radiator if we had a thin, short, thin, wide, short. Let's go short. If we had a short radiator like this, we want to bring the coolant in on one side and have it go all the way across and then out. Both the vertical flow and the cross flow radiators that we've talked about are what's called a single pass radiator, where the coolant passes straight across, so from one side to the other, from the top to the bottom. There's also double pass or two pass radiators, and in those there's also triple pass radiators. And a double pass radiator, let's say the coolant comes in here, the core will be divided into two halves and the coolant flows across one half and then back through the other half. So the inlet and the outlet would be on the same side. In a triple pass design, which is kind of like an S shape, the coolant would flow across here, would be divided into three, back over here, and then finally back over to there, and we'd have an inlet on one side and an outlet on the opposite side. That gives a greater amount of time spent in the radiator, maybe more efficient cooling, but it requires a bit more pumping pressure to actually force the coolant along that sort of more convoluted pass. Now, flow rate is very important for radiators because the critical thing in losing heat from coolant is the temperature difference between the coolant and the air. If the coolant's only a couple of degrees warmer than the air, there's not much cooling taking place, which makes sense, it's kind of sensible. But when it's a huge difference, say the coolant's 100 degrees and it's minus 20 outside, there's a massive difference between those two temperatures and heat is going to be pouring out of the coolant. That's what we want. This means that a fast flow of coolant through a small radiator is going to be better than a slow flow through a big radiator. And the higher flow rate that we've got there also comes at the cost of running the system under higher pressure. Now, there's a trade-off because if you force coolant very quickly through a radiator, it spends hardly any time inside the radiator. So there's some fluid thermodynamic nonsense to be calculated on computers there. Radiator design depends really on three things. It depends on the size of the engine, the climate that it's being operated in, and the way the vehicle is being used, what its intended purpose is. When it comes to sizing a radiator, there's really three critical numbers. We've got the width and the height of the radiator, and then we also have depth, which is the number of rows of tubes. Now, width and height are basically constrained by what's going to be available in terms of space inside that vehicle, what's available under the hood. A greater cross-sectional area can be achieved by angling the radiator backwards. So if you imagine we have our radiator here, if we have the radiator at this angle, 90 degrees, straight up vertical, we have this certain area in contact with the air, so the airflow is pouring through in this direction. If we angle this radiator back like that, now we could have a much sleeker frontage to our car, and we still have the same surface area being covered by the airflow through the vehicle. So that's one thing that manufacturers can do, is to angle the radiator. You'll see that on Formula One cars, where on the sides of the vehicle in the cooling pods, the radiators are angled to get that airflow through at an angle, but without increasing the frontage, the cross-sectional area of the vehicle, which is forcing its way through the air. So vehicle designers do serious computer simulation to work out the radiator sizing needed for a vehicle. But there's also a much simpler kind of rule of thumb type calculation that you can find online for calculating radiator size, and it's pretty interesting. So using that formula, basically you start with the engine size in cc or cubic inches, and then you apply various factors to that number to give you the volume of radiator needed. So it looks at things like the airflow through the system, the number of fans, the number of rows in the radiator, the material of the radiator, that kind of thing. Now, in terms of mounting the radiator into the vehicle, when you buy a new radiator, you'll find that the old radiator is mounted usually with some rubber grommets or some saddles, some piece of rubber that isolates the radiator from the vibration of the vehicle. Your replacement radiator generally won't come with these rubber grommets, so you need to swap them over. Don't forget to do that. Now, the movement of air through the radiator is the key to effective cooling here. The vehicle's grille and the bumper here are going to be designed to deflect air into the radiator. Now, a lot of the plastic on the front of a vehicle that fits around the bumper and the inside and around the grille, they're very carefully designed to ensure that the right airflow goes through the radiator. Now, airflow through the radiator works by having a difference in pressure between the front and the back of the radiator. So when you're driving along, we want an area of high pressure in front of the radiator, which is created by the vehicle pushing on the air. And basically, the vehicle is ploughing the air, piling it up in front and creating high pressure. And it's obvious. But what's maybe not so obvious is that we want an area of low pressure behind the radiator inside the engine bay. And this is why underneath the vehicle you have plastic trays under the engine, and those are designed to guide the air away from going back in underneath the radiator and then filling up under the bonnet. Kind of like if you imagine dragging a carrier bag through the air, the bag fills with air and you end up with a high pressure in there. That's what you don't want in the engine bay, because what happens is people tend to take those trays off. So all the time, somebody goes to change the oil, a couple of the screws or the fixings are corroded, the under tray doesn't quite go back on, and they think, oh well, it doesn't matter, I wash the car regularly anyway and it's probably only there to keep mud off the bottom of the engine. It's not true. Those trays are there to guide the air under the vehicle, to take it past the engine compartment and stop it building up inside. Because if we've got a big area of high pressure air in here, no matter how strong the fan and really no matter how quickly we're pushing forwards, if we've got high pressure on this side and high pressure on this side, then the air won't flow through the radiator. So those plastic under trays are important for actually keeping the cooling going. So normally the passive airflow that comes from the vehicle moving forwards through the air is going to push air through the radiator. And that makes sense. The faster the engine is running in a normal situation, the faster the vehicle is moving, the more air is flowing through the radiator, the more effective the cooling is. But there's certain situations where the engine's working really, really hard, but there's not so much airflow coming through the radiator. So two obvious situations, quite commonplace. One is if you're climbing a long mountain. The engine's working hard, you're in a low gear, you're really ploughing up that hill, but you've not got a huge forward speed, you don't have great airflow through the engine. A second situation would be towing a trailer. Again, the engine's working much harder than normal, but you're not moving that quickly, and so there's not that boost of airflow coming through. So there needs to be a way to create extra airflow through the radiator even when the vehicle's stationary or it's not moving very quick. That's done by the fan, which we'll get to next.